Okay, we're back now to go into carbs, lipids, proteins, nucleic acids. Um, so at this point, we've covered um, the basics of organic chemistry, looking at hydrocarbons as our principal model of um, organic molecules. And then we looked at functional groups, um, and we connected functional groups to those hydrocarbons um, to show that by changing their structures, we also change their functions, and we use propane as a model to show how we can add functional groups to hydrocarbons. Okay, so now we can get into the principal molecules of life. Beginning with the carbohydrates. All right, so most students know that carbohydrates are like these high calorie um, foods portions, right? Like pastas, rice, candies, drinks. They're all loaded with carbohydrates. But as you're going to learn in this lecture, carbohydrates come in two broad forms, all right? They come as simple carbs and they come as complex carbs. And uh, some carbs are good for you, too many carbs are bad for you, okay? But I have two very common carbohydrates of life shown here, glucose and fructose. Let's practice our functional groups, right? I think that the functional group that you should pick up on right away that is very common in carbohydrates is alcohol. You can see alcohols are very prominent in both glucose and fructose. Do you notice the ones that are shaded in blue? Can you tell me what those functional groups are? You might remember that this one over here is a good example of an aldehyde. But what do you call a double bond oxygen to a carbon in the middle of the chain? I hope you figured out that that was a ketone. Okay, here's something interesting. If you count all the carbons in both glucose and fructose, you will see that they both have 6 carbons. You can see them counted here. Uh, if you then look at the number of hydrogens in glucose and fructose, you will find that they both have 12. And if you count the number of oxygens, you'll see that they have 6. Okay, they both have the same chemical formula. They both have the same molecular formula. But do they look the same to you? They don't. So these two, glucose and fructose, are examples of what we call isomers. All right, if you knew that word as I was developing this information, you're doing great, okay? If that word didn't come up right away, but you knew that you had heard this before, okay, you're growing, you're developing your understanding of this type of chemistry. Okay, so let's get into simple versus complex carbs. Okay, what you're looking at here is a model of what glucose actually looks like in nature. So this glucose that we're showing you here in the linear form, this one here, is not really the way it looks in nature. It looks more like this very busy looking molecule. But this is the way we actually want you to know it. We want you to know the simplified version of it, right? We don't need all this other busy information, the blown up version of it. We don't need it. From here on out, if you see this, you should know that's an example of a simple carbohydrate. It's one ring. In fact, if you should see two rings attached to each other, like this, that's still an example of a simple carbohydrate. For example, here. Here's glucose in its very complicated, detailed form. Here's another glucose. And then notice what we did here. We took away the alcohol and the hydrogen, pulled them out, made water. And now this oxygen and this carbon over here in the corner are missing a bond each. And so they will stick to each other using that oxygen in the middle. And you will go from single rings to two rings. Everything that you see here, single ring or double ring down below in the case of maltose, all of these are examples of simple carbohydrates. All right, so let's summarize. What do we know about simple carbs? Simple carbs can exist as single ring structures, like that, or they can exist as two ring structures, like that. The single ring structures are called monosaccharides. Monosaccharides. The two ring structures are called, appropriately, disaccharides. That literally says single sugar, double sugar. That's what that says. Saccharum, saccharides, sugars. Okay, you can link a variety of different types of monosaccharides together to form a variety of different um, um, disaccharides. So for example, if you link glucose and fructose together, you will create this. Notice how fructose looks a little bit different from glucose. They have the same exact chemical formula, but their shapes are different. But if you link these two together, you will then create the following. This is called sucrose. This is table sugar you have at home. So the table sugar you have at home is 1/2 glucose and 1/2 fructose. And what's really interesting is that fructose by itself is actually sweeter than sucrose. Think about what I just said. Fructose by itself is a little bit sweeter than sucrose. And what if I told you that this guy has half the calories than that guy? Do you see why fructose is used as a sweetener? For one, it's easier to make. Fructose that you get in your sweeteners come from cornstarch specifically. So they're called high fructose corn syrup. And we use that to sweeten all kinds of drinks today. And you get more sweetness and less calories, potentially. All right. So then what is the issue with high fructose corn syrup? Okay, we'll talk about it maybe in a second. All right, so if you link glucose with glucose, as you saw over here, you create maltose. And maltose and sucrose have the same chemical formula, but they look different. And maltose is used to sweeten a lot of candies, and it's also used to make malt liquor, maltose, malt shakes, maltose. See, the names of these things that you have experienced in life maybe are rooted in the language of chemistry, organic chemistry. You can also link a glucose with a galactose. Here's glucose. And you can link it to a galactose that looks very similar to glucose. And you can create a milk sugar called lactose. This is what makes milk have a slight sweet taste to it. It's the lactose. Okay, so sucrose, lactose, maltose, all of them, along with glucose and fructose, all of these are examples of simple sugars, and all of them have some things in common. They all taste sweet, and They are very quick sources of energy. Okay, that's what you want to know about simple carbohydrates. You want to know that they can exist as monosaccharides, disaccharides, right? And you want to know that they can taste, that they will taste sweet and that they are quick sources of energy. And we'll do a lab on carbohydrates also. Okay, that's simple carbohydrates. Um, Here's a little bit more on high fructose corn syrup. So high fructose corn syrup is interesting because it's 55% fructose versus 45% glucose. So what do I mean by that? Well, here is um, sucrose. Sucrose is table sugar that comes from sugar cane, and that guy is 50% glucose and 50% fructose. But high fructose corn syrup is only like 5% more fructose than glucose. And somehow it's supposed to be bad for you. Okay, there may be something to how fructose um, interacts with our physiology, our, in this case, pancreas, uh, and its role in stimulating insulin production, right? Um, so, as you may or may not know, whenever you eat carbohydrates, simple sugars to be specific, your pancreas reacts by creating insulin. And that insulin travels throughout your body and it alerts your body that there's sugars present and that they should open up little doorways to bring in that sugar and feed themselves, right? So that's what simple sugars do. And some studies might indicate that fructose doesn't really stimulate the production of insulin as well as other sugars do, like sucrose. But what I want to focus on is this idea that high fructose corn syrup is the cause of obesity. That was the prevailing idea through the late 80s and 90s. But here's what we found out. First, the idea was developed because as we continued our use of high fructose corn syrup, obesity started going up. However, when we started reducing high fructose corn syrup, when we started using less of it, obesity kept going up. So we reduced the use of high fructose corn syrup and still obesity kept climbing. So I think what that tells us is okay, obesity is affected by other things, not necessarily just high fructose corn syrup. I'm sure high fructose corn syrup is a problem, but it's not the only problem, and it doesn't seem to be the most important problem because obesity is still going up. So I think we all understand that obesity is a complex phenomenon, right? The U.S. is the country with the highest rate of obesity. We are the largest group of people on the planet, and that's just crazy to say. And it's because of our lifestyle. We have high calorie meals and a very, very low activity lifestyle compared to other populations, right? So that's the problem we have. We have high calories and very low exercise or very low physical activity. Our jobs are like sitting around and, we eat and we don't put those calories to work. Here's a way to infuse perspective here. The World Health Organization says that, the average person should consume like 20 pounds of sugar a year. So they just mapped out the whole year. This is where you should be around. But our Food and Drug Administration has blown that up to twice the amount. The Food and Drug Administration has said, no, you can go up to 40 pounds of sugar. Think about the grocery time in your life. Like, think about the time you go to the grocery store. And now think about the cereal aisle and grains. Um, that's a lot of sugar, lots and lots of sugar. And you can then also think about um, all the other sweet stuff out there, the ice creams and so on and so forth. This is what the average American consumes actually, 130 pounds. Like, that is no joke. Like, sugars are a massive component of our diet. Potatoes, fries, chips, right? They're so bad for you. Uh, a little bit is important in your life. It gives you energy, and you need that. You need quick sources of energy, right? To stay alert during lectures, right? Um, but we overdo it. And you know you overdo it if after a meal, all you want to do is take a nap. Like, you probably ate a high calorie meal, and your body's like, okay, look, I don't know that I have the blood to send to your brain. I think right now I need that blood to go to the digestive system because I got a lot of digestion to do. Think about that. And then think about those chicken fingers and fries that we sell at the campus Lion's Den. High calories. You don't want that just before you go into a math lecture or a science lecture. You need your brain to be like humming along, right? Have the peanut butter and jelly instead. That's quick sources of energy. It's easier to digest. It doesn't take a lot of like energy, blood flow going to your digestive system, right? Something light, quick, right? Something clean, right? Better yet, prepare your own lunches. All right, I would have talked about this more in lecture as an enrichment thing. I want to move on now to complex carbs. Okay, so what do you notice immediately about complex carbs? They're not one or two ring structures, right? Here's one, that's a simple carb. Here's a simple carb. And then those two, if they are attached, that's a simple carb. But what if you add like hundreds? Then they start spiraling, right? That's starch. That's what you find in plants, right? Specifically potatoes, loaded with starch, right? But so are other things like carrots, right? Uh, Yams, sweet potatoes, all of those loaded with starch. So, starch is the way that plants store lots and lots of sugar. They store them in a very large, long molecule, okay? But it turns out animals, like you and I, we do the same. We also have our own version of starch. You can see it here. It's called glycogen. It's a very long, spiraling molecule, but the only difference is that we also branch out. That's it. That's the difference. We make starch, but we branch out, and now we call it glycogen. And you store your glycogen in your muscles, and you store a lot of it in your liver also. That's a reserve for when you need sugars. Um, Athletes that train for marathons or long endurance activities like triathlons or long cycling races, right? Tour de France, for example. All of those athletes know to do something called carbo loading. And what they're doing is they're eating a ton of carbohydrates the days leading to their event because they're trying to load their muscle and their liver with glycogen so that when they burn through their simple sugars that are floating in their bloodstream in the early stages of their activity, they will have a ton of other complex carbs that are breaking down a little at a time, releasing simple carbohydrates to feed your cells. That's the strategy behind carbo loading. Some athletes will even have like um, a small half of a potato uh, in their stomachs, so that while they're riding, they'll have another reserve of carbohydrates. So they have the simple carbs that are in their bloodstream right now. They'll have the complex carbs that are in their muscle and their liver, and then they'll have another chunk of potato in their digestive system waiting to also be digested and broken down through what reaction? Do you remember? If you said hydrolysis, you're on it. Yeah, so that's like that is like major strategy, carbo loading. All right, so what do we know about complex carbs already different from simple carbs? Simple carbs are one or two rings, monosaccharides, disaccharides. But complex carbs, these are polysaccharides. They are very, very long chains. And they do not taste sweet, and they give you what we call intermediate sources of energy. They are not fast. They take longer to break down, right? And they're not giving you the energy right away like simple carbs do. Okay, here's something interesting. You might be a student that ends up going on a nature walk with me. And if it's a rigorous one, and they tend not to be, but if it should ever be a rigorous nature walk, I would recommend that you come with trail mix. And trail mix is usually a blend of three energy rich molecules. Simple carbs. The simple carbs will give you the energy right away. Those would be like the M&Ms that are in the trail mix. Simple carbs, monosaccharides, disaccharides, they give you the energy right away. The reason why a Snickers satisfies you is because it gives you the energy right away. But then you crash. Like if all you had was sweets, the energy is delivered right away and then you burn it right away, so you crash. So if you need energy right away, okay, but understand that you're also going to be burning through it so fast that you're going to like crash and you're going to need energy again. But trail mix also gives you things like nuts, and nuts have um, complex carbs in them, and they also have lipids. And lipids are the next biomolecule we're going to talk about. Lipids are like long term stored energy. So, trail mix is a blend of simple, quick energy, starches, intermediate energy, right? Energy that keeps coming a little at a time throughout your nature walk or throughout your rigorous hike, and also lipids that will be there providing you energy, right? As you continue, as you sustain your activity, right? So you're on this nature walk and you're feeling a little bit like, okay, I'm like feeling like I'm getting tired. I could use a little pep in my step. Throw in the handful of trail mix. You're going to get immediately a boost because of the simple sugars in the M&Ms and the raisins and things like that. But as you continue going, you'll burn through that and you won't feel it because now the complex carbs are delivering energy, keeping you going. And then as those start to be depleted, then the lipids kick in and then they start giving you energy also, right? So when you start feeling tired again, that means, okay, I burned through all of that. Now I got to get a little bit more. So you throw in a little bit more trail mix. Trail mix is great on a trail. You know where trail mix is a disaster? When you're at home in front of the TV, right? Melted into your couch or into your bed, and you're throwing in high calories and not doing anything with them. That's our American lifestyle. Okay, so we've covered the complex carbs. Notice that I haven't talked about cellulose down below. All right, what is cellulose? Cellulose is a very important um complex carb or polysaccharide. This is otherwise known in society as fiber in your diet. This is what you get from eating salads. Fiber in your diet is very important to helping you with digestion and also to reduce the amount of sugars and lipids that you absorb. If you have a salad at every meal, you're actually going to reduce the amount of sugars and the amount of lipids that your body absorbs from that meal. So having salads is great. And it gives you the additional fiber that helps you with digestion so that, next time um, you're at the restroom going number two, it's a comfortable situation, right? Okay, so where have you seen fiber? Like actually seen it? If you ever take a celery stalk, snap it in half, and then pull it apart, and you see those stringy fibers, that's cellulose. That's a lot of cellulose. You can see it with the naked eye. That's this stuff. and a lot of it. That's the fiber that you would see in celery. Okay, so let's see. We're going to make a table. And this table is a good tool to process a lot of information and put it into a geographic form that makes sense. Okay? So here's a table that I propose you do. I want you to break up the table into plants versus animals. This is a table that covers polysaccharides. And I want you to think about them as nutritional polysaccharides versus structural polysaccharides. So, nutritional polysaccharides are the ones that you actually consume and you get energy from, nutrition. So, plants give us starch, whereas animals give us glycogen. Those are the nutritional starch and glycogen. But then we added also cellulose, and cellulose is not something you break down for energy. The way you ate cellulose is the way it'll come out in your poop. So that's cellulose. It is not nutritional, it is structural. Plants use it to create structures. Again, this is fiber in your diet also. Do the animals have their version of cellulose? Yes, we do. It's called chitin. And chitin is found in interesting places like insect shells. Interestingly, insect shells are made out of sugars, but you'll get zero nutrition out of it. This is why we don't eat them. You can also get them in crustaceans, lobster, crab, shrimp. The shells that they have, those are also made out of sugar. But you can't break them down. You can't do anything with them. They're structures. They're not nutritional. And finally, you can also get them in fungus, specifically something called a cell wall. So fungi also have this polysaccharide that doesn't give you any nutritional value. It forms sort of a protective structure around fungal cells. Okay, so that's the table, and this is the outline form of that table. Outline forms are really good for presentations, but they're not very good for remembering things. Tables are way better for remembering things. So make that table right there, put it on a flashcard, call one side polysaccharides, and then put the table on the back side, and then just keep looking at it. It's so much better than having multiple flashcards looking at each one of these. That's 4 different flashcards where you can just have one. And it's geographic. So that when you're stressed out, you're like, oh yeah, I had plants on the left, I had animals on the right, and then I had starch. That's in plants. I think I knew that already. Below that, that would have been cellulose. For animals, I have glycogen, and below that, I have chitin. And then you have all this information geographically organized in your brain, and it's so good when you're stressed out the day of a test. Okay, so we've covered the carbohydrates. Let's move on now to lipids. All right, so lipids are long-term stored energy, right? Our bodies are sort of designed to store energy long-term in the form of lipids. The more lipids you have, the more potential energy you have. That's not a bad thing, right? If you have too much of that potential energy and you're not really doing anything about it, that can be a bad thing, right? But having some, fat around your waist, that's not terrible. Everyone wants to be like super lean, cut, defined, and all that, right? Um, and that should be like, okay, yeah, temporary, right? But you kind of want to have like some sort of calories in the event that you should need them, right? You want to have a little potential energy there. All right, so lipids. Um, Lipids are going to look very similar to long chains of carbohydrates, right? Here's what I'm talking about. I'm talking about like this. See that long chain of glucose and fructose? Lipids are going to have that sort of look to them, right? Here's the goals to understanding lipids. I think you already know one thing. It's long-term stored energy. But the other thing you want to know is that lipids can exist in what we call saturated and unsaturated forms. Saturated fat is solid at room temperature, and unsaturated fat is liquid at room temperature. And one of those is better than the others for us overall, okay? So let's get to understanding saturated and unsaturated fat by looking at one of the most common fats in our lives. This is the triglyceride. Okay, let's break down this word, tri. I think you know that that means three. Tri. Here we go. 1, 2, 3. Glyceride. Okay, that's referring to this glycerol. But look at glycerol by itself. This is it right here. Let me clean it up. That's glycerol. Do you notice that it's made up of 3 carbons? Propane. And do you notice that every carbon has what functional group on it? Alcohols. See, alcohols are everywhere, right? Okay, that's glycerol. That's propane. That's the fuel that you use on your grill. But if you add alcohols to every one of those carbons, now it's glycerol. And glycerol is a component of triglycerides, which is that fat that's in our diet. Lard, butter, vegetable oil, right? Change the structure and you change the function, right? They're chemically different now and they have different properties. Okay, so that's a glycerol. So if you attach one glycerol to 3 fatty acids, 1, 2, 3 fatty acids, here's a fatty acid. Let's look at the fatty acid a little bit more closely. Look at what the fatty acid is made out of. It's just carbons and hydrogens, carbons, hydrogens, carbons, hydrogens, carbons, hydrogens. And then at the very end, it's got this functional group. Do you recognize it? It is called a fatty acid. Let's break down that term. Why is it fatty? Well, if you look here on the highlighted section, that's just basically this. Carbons and hydrogens, and at the very end, you'll have 3 hydrogens. So basically, I've drawn this little section right there. That's just hydrocarbons. And what did we learn about hydrocarbons? That they are what? They don't mix with water, like fat. So that's where the term fatty comes from. It's this highlighted section in gold. Why is it then called an acid? Well, that's because of that functional group. Did you recognize it? If you said carboxylic acid, that's what it is. So that's why it's called a fatty acid. And if you attach 3 of those guys to a glycerol, what is the reaction that you're using to do that? Let's clean it up so that you can see it a little bit better. What's the reaction that we're using? Are we building or breaking down? We're building. So that's dehydration synthesis, and you can see the dehydration and you can see the synthesis here where you attach them together. All right, so this is a triglyceride. Okay, triglycerides are very common in our diets. They're the vegetable oils, olive oils, corn oil, canola oil, butter, lard, right? That white stuff, the white fat in a steak, that's triglycerides. That's this guy. So what makes them liquid versus solid? Okay, this one right here would appear solid at room temperature. This one would appear solid at room temperature. This one would appear solid at room temperature. But this one right here would be a liquid at room temperature. What's the difference? Very simply, if you just saw a long straight chain, that's saturated fat. If you see the chain with an angle, that's unsaturated fat. This triglyceride right here would be considered monounsaturated. Why? Because it only has one bend. And that bend, do you notice something interesting about it? Do you see that it has a double bond right there? That's also why it's monounsaturated. What if there was another double bond here? What would happen then? Then the chain would bend again, right? So you could have, for example, a triglyceride that has this shape. I'm just simplifying it now. See, all three fatty acids are straight. This would be saturated fat, solid at room temperature. But what if you had this kind of fat instead, with a bunch of double bonds, creating a bunch of bends and different angles? This would be polyunsaturated because it's got a lot of different turns. So this is polyunsaturated fat. It would definitely be liquid at room temperature, and it's way healthier for you versus this. Why? Well, because saturated fat tends to pack really tightly. You could put another saturated fat right here, right on top of it, and more saturated fat right next to it, like boxes. You could stack them up like boxes really easily. And when you do that in your bloodstream, especially in places where the blood flow branches out, that kind of fat right here likes to attach itself right here. And the more fat you eat and you don't burn down, starts creating a plaque. And that plaque prevents blood flow from going through there so easily. So your heart now needs to pump harder, more frequently, and your blood vessels start to bulge to make way for the increased pressure your heart is exerting to pump the blood past that fat plaque. And now you've got cardiovascular issues. That's a disaster in the making. Unsaturated fat, on the other hand, uh, is digested easier, and because it has all those angles, like these angles here, it prevents the fat from packing in really tightly. It's like a box that has weird angles to it. You can't stack those boxes so easily. They roll over each other, and that rollover effect, that's liquid. Okay, what's a triglyceride? A triglyceride is made up of two things. One glycerol plus three fatty acids. If the fatty acids have no double bonds in them, right? They're going to appear straight. That's saturated fat. If there are double bonds in at least one of the fatty acids, you are now considered unsaturated fat. This is a good example of unsaturated fat. Specifically, it's monounsaturated because it has one bend, and that bend is attributed to a double bond, right? So let's clean this up so we can see them clear. All right, here's what I want to show you. Do you notice that every carbon in the straight chains, I'm going to use red here. These straight chains, do you notice that every carbon in the middle, every carbon has two hydrogens? Every carbon in the middle comes with two hydrogens, right? But now look over here. Do you see that Each of those carbons is missing a hydrogen, and they've replaced the hydrogen with a double bond right there. That's the difference. To be saturated means to be full. Full of what? Full of hydrogens. Two hydrogens, to be exact. What does it mean to be unsaturated? That means that you're not full. Those are examples of two carbons that are not full. Each one of them is missing a hydrogen. They're not maxed out. The maximum amount of hydrogens you can have in the middle of a chain is two, right? You might remember carbon can make four bonds. All right, so here's the chain that way, here's the chain this way. These carbons right here, they already have one bond, two bonds. They can only have two extra bonds, one to each hydrogen. This carbon right here has one bond there, one bond here, and so it can only have two other bonds for hydrogens there. But what happens if you take away the hydrogens? Well, then they respond by doing what? Double bonding. And when they double bond, it causes this carbon here to change its orientation, and now the chain, instead of going this way, now it goes this way. Introducing double bonds changes the shape of the molecule, change the structure, and you will alter its function, right? Instead of being saturated, now it's unsaturated fat, and they act differently inside of our blood vessels. Okay, in summary, lipids are energy molecules. We like to store them long term. They provide energy in the long run. They're kind of like a savings account, right? We don't want to touch them unless we absolutely have to. And the most common lipid in our diet is the triglyceride, made up of one glycerol with three fatty acids. The fatty acids are interesting because the fatty acids are made up of largely carbons and hydrogens, so they're a hydrocarbon skeleton. If every carbon in the middle has two hydrogens, then you are saturated, you are full of hydrogens, and you will appear like that. If you have missing hydrogens, then you replace the missing hydrogens with double bonds, and that changes your structure. Now you are unsaturated, and you can be monounsaturated if you only have one double bond. Or you can be polyunsaturated if you have multiple double bonds. Right? Every one of these bends represents where a double bond has produced the bend. That would be polyunsaturated. So take a look at the lipids that you have in your kitchen. Look at the breakdown. They'll tell you polyunsaturated, right? Monounsaturated fat. It'll tell you the percentages of each. Okay, there are variations to this, okay? For example, I don't know if you know this or not, but just because you're an animal, that doesn't mean that all your fat is saturated. Here's an example of a very common fish eaten by health-conscious individuals like myself. This would be salmon. And salmon doesn't store its fat the way beef does. Beef stores its fat um, in a solid form. Most animals do. The vast majority of animals, we store our fat in this solid white form, but not salmon. Salmon is an oily fish. Salmon stores its fat like in oil instead. That's interesting. And also, you should know that some plants don't store their fat like oil. Some of them store it like a solid. Have you seen coconut oil? Is it really just oil, or are there solid portions in there? And if you break down those solid portions, right, that's like saturated fat. Palm oil, same thing. So next time you're eating something that has coconut oil, palm oil, know that you are consuming saturated fat. And just because it came from a plant, that doesn't make it healthy, right? Here's some things to understand. Saturated fat, right, will elevate your risk for cardiovascular issues like heart risks from a risk of one, consuming bacon, meat with fat in it, saturated fat, will elevate your risk 17%. But if you consume monounsaturated fat, like the one we were looking at here, like this guy here, you will reduce your risk by like 19%. And if you consume polyunsaturated fat, you will reduce the risk by 38%. So I think that you want to be doing this, right? Consume fats that are in this form. Where do you get those kinds of fats from? Nuts are a very good source, right? I wouldn't say necessarily like cooking oils. Some cooking oils are good, but nuts are a very good source of, and so are fish, very good source. So replace, the protein in your diet with fish. If you're eating like steak, maybe graduate to chicken and then eventually get to fish if you don't like fish all that much. But definitely reduce red meat. What happens if you eat foods that have trans fats in them? You elevate your risk 93%. That's almost double the risk of heart issues. Where do you get trans fats from? Okay, any food item that says that it contains partially hydrogenated oil, this is basically this kind of fat. Let's clean this up. It's basically good fat from vegetables that has been turned into bad fat by doing a chemical reaction called partial dehydrogenation. All right, I don't know about you, but that was kind of therapeutic doing that erasing. All right, so here's an example of a good fat. All right, this one is polyunsaturated. The chain is doing all this sort of stuff. Lots of double bonds. Very good fat. And then somebody says, you know what? This oil isn't all that marketable. It's just used for cooking. But what if we could use it to spread it on toast the way we do butter? But it isn't butter, right? So it would be better because it's derived from plants. It's, a good fat. But to make it solid so that you can spread it on butter, right? What do you have to do? You have to add hydrogens that are missing. Remember that the bands are caused by double bonds where hydrogens are missing. So you have to put hydrogens back. So if you put hydrogens back here and you make that CH2 and CH2, that chain is going to go from having a double bond and changing the angle, it's going to go back to this. But isn't that saturated fat? That's exactly what you did. You created saturated fat. But what's interesting is also this. Some of those hydrogens that you put back in there don't turn the entire chain straight. There'll still be some bends. There'll be fewer, but there'll still be some bends. But where those bends are happening, something interesting happens. The hydrogens appear on opposite sides, as opposed to the hydrogens appearing on the same side, like they might appear there. So that CH here, that CH is that CH, and this CH is this CH. But if you put hydrogens back and the H's are now on opposite sides, this kind of situation is called cis fat, very common in nature. This is called trans fat, not so common in nature. And what does trans fat do? Increases your heart risk to double the amount. So you need to look in your cookies, any food item, look in the back nutritional label. And if you see that it contains partially hydrogenated canola, partially hydrogenated corn, partially hydrogenated safflower oil, anything that is partially hydrogenated has gone through this reaction and it's created trans fats. And even if it says that it contains 0% trans fat, you should know that that's not true. The Food and Drug Administration, the same one that said you could double up your sugars, they also say that you can claim 0 gram trans fat if one portion of what you are eating has half a gram or less of trans fat. You can get away with saying that you have 0 gram trans fat. So imagine you're eating cookies, right? Like you just bought a cookie bag, and in the back it says it contains partially hydrogenated oil, but when you look at the nutritional label, it says 0 grams trans fat. But the bag of cookies, like maybe a bag of cookies you got from the vending machine, says that 2 cookies is the serving size. Well, those 2 cookies might have half a gram, 0.5 grams of trans fat. And that bag might have like 4 servings. Do you follow where this is going? 2 cookies, that's 1 serving. You get half a gram. The bag has 4 servings. You would have eaten the whole bag. And if you ate that whole bag, you just got 2 grams of trans fat. Congratulations. Your heart just took a hit. If you're a fan of Costco, if you ever had their Costco hot dog, you might want to stop. Next time you're at Costco, look at the bag of Costco hot dogs in the actual refrigerator, not the ones that you're buying. But look at the ones in the refrigerator, the ones that they're using to make the hot dogs. They got trans fats in them. Okay, the other kind of lipid I want to talk about, we're going to wrap up this lecture, is a phospholipid. The phospholipid has a phosphate group, and then instead of having 3 fatty acids, so here's the glycerol, here's the fatty acid. So now I'm drawing it differently. We're not drawing it horizontal, we're drawing it vertical, right? But that's no different from this, right? Don't be confused. I just flipped it to that. But if I were to go back there and remove one of the fatty acids and replace the fatty acid with a phosphate group, that's this guy. And we just simply draw it like this. That's now a phospholipid. See the phosphate? That's a functional group. That's a phospholipid. And you should know that phospholipids are important in membranes. I want you to put those 2 words together. Phospholipids and membranes go together. Okay, and then the last lipid we'll talk about, and we'll end the lecture here, are cholesterol, which is important in your diet. You need it because cholesterol is used to make steroids. So you do need cholesterol. If you're a male, you're going to eat cholesterol and you're going to turn it into testosterone. If you're a female, you're going to turn it into estradiol, or what most people simply call estrogen. And look at cholesterol side by side. Do you notice that the cholesterol has the same 1, 2, 3, 4 rings? All of those are hydrocarbons. All those rings are made up of carbon and hydrogen, and that's it. Do you recognize this functional group? You should have said alcohol. Do you recognize this guy? Haven't seen that for a while. That's the methyl group. Do you recognize the alcohol there also? HOOH, same thing. And do you recognize this guy? It's in the middle of the chain if it helps you. That's a ketone. All right, so look at the name, testosterone, because of the ketone. Estradiol, because of the alcohol. That's where those names come from. All right, cholesterols lead to the formation of steroids, and steroids are very powerful hormones that help, for one, masculinize or feminize an animal, right? Testosterone changes your body plan development to being male. Estrogen changes it to being female. So they're very important. So now lipids have a variety of functions, don't they? Lipids are not just nutritional fats like triglycerides, but they can also be structural fats that form membranes, like you're seeing here. That's a membrane. And they can also be powerful steroids. So lipids now have more functions than carbohydrates. Okay, we'll stop this lecture here.